Hello, thanks for coming. And today I'm going to talk about a joint submission with Masahito Hayashi and Haojun Chen. I will have two parts. The first part is about the channel resolvability, and in deal with this problem, Masahito Hayashi he introduce a new version of quantum Shannon theorem. That's what I'm going to talk about. So let me start with the concept of channel resolvability. So suppose we have a classical quantum channel. Basically, you just assign every letter in alphabet's quantum states. Then you can also talk about random outputs. Just you have a probability distribution P, and then you do this convex combination of the deterministic output. Then the channel resolvability is a question trying to find the minimal codebook such that the average of the deterministic deterministic output of the code word will be approximating the probabilistic outputs. That's what we want to do. Then one can also formulate the question in other way. Instead of asking the smallest cardinality of the codebook, you can ask if given a size of codebook, how small the error we can achieve. Then one can introduce in this minimal distance between codebook average of M size codebook output with the actual probabilities outputs, and taking info of all possible codebook. And using the concept of M-type probability distribution, which is the distribution values that only take fractions like 1 of M, 2 of M, then you can reformulate these questions approximating general channel outputs by channel outputs coming from M-type probability. And this question can be formulated in two settings. The first setting is that you have fixed inputs. You just want to approximate in that outputs. Or you want to consider the worst case to consider the largest possible error in the approximation. So that's the setup. So this is an illustration of pixel image that if you increase the resolution, the picture becomes clear. That's approximating the shape better. So the question we want to know is that how large the resolution is needed to approximate the channel's output. And in the standard information theoretical way, we formulate this asymptotic achievable rates. It's just the smallest rate R, such that whenever you add a little bit small rates, in average, if you use 2 to the n R plus gamma cardinality codebook, basically R plus gamma bits per channel, then you are going to achieving a vanishing error. And this is for the fixed input. You just have the input to be the IID product of the same input. Or you just take the worst case for your IID copy of the channel. So this question can be formulated in these two settings. Then our main result is that we characterize the rates in these two settings. The rate for the fixed inputs case channel resolvability is given by this mutual information of the joint input-output, joint input channel output states, and then taking an informal of all the input that output the same states. This is natural because when you approximate in a state, you don't care about which input produces it. And in the worst case, what we have just taking the mutual information informal of all inputs. In that case, we all know this is just the channel capacity or the whole level quantity for the classical quantum channel. Moreover, we'll be able to show that if you're trying to do the resolution below this asymptotic rates needed, the error in terms of the trace distance will goes to 1. So basically, we have a strong converse for these two tasks. So this is the main results. Before I mention the proof, I want to just briefly remark on the history. So this question was first considered for classical channel, which first introduced by Van and Verdu, and they basically figure out the achievability results. And then in a 2006 paper, by Masahiro Hayashi, he point out there's some issue in the strong converse part. So he come up with other arguments in the vortex input setting, and in the paper with Professor Watanabe and Hayashi, they get a second order and also the fixed input setting in a 2014 paper. And this channel resolvability has been studied for its connection with identification codes, rate distortion, and also in the application of wild-type channel. And in the CQ setting, this concept has also appeared in the work by Luber in 1999, and later also considered by Hayashi. And they have been, this idea of approximating channel output has also appeared in the Devitax paper calculating pure and private and quantum capacity, and also later, and also another work by Chai, Winter, and Young. And in the quantum to quantum channel setting, this problem recently has also been considered by Atif, Prandaham, and Andreas, and also a follow-up paper. But I want to mention that in the communication case, the capacity of classical quantum channel can be considered as a special case of the entanglement breaking channel in the quantum to quantum setting. But for this resolvability problem, these two, the CQ channel cannot reduce to entanglement breaking channel. The reason is that when you consider the resolution, you count how many the code word you use. If you just use one deterministic quantum input, which is a pure state, and you put into these measurements, which is how you implement in a classical quantum channel into an entanglement breaking channel, then you can create a random output. You can create a randomized classical input. So in that case, so these two problems has a complete different setting. Actually, in this work, they characterize that if you want to ask what's the quantum to quantum channel resolvability, it goes to the negative conditional entropy, which for classical quantum channel is always negative. So it does not make sense even in this case. So these two, the CQ channel and entanglement breaking channel, in terms of resolvability, they are completely different. Okay, so this is our result. Let me mention what's the proof ingredients. The first case is the fixed input setting. For the achievability, we use a tool called soft covering, which developed several years earlier. And then for the strong converse, this is the part, this is the most difficult part where Masahiro Hayashi come up with this new version of a quantum Shannon theorem. And for the worst input setting, if we first solve this in the paper using the information spectrum method, later we find out actually one can also use the soft covering to do the overall achievability. And for the strong converse, this is essentially already known from the Luber's paper in 1999, using the idea of identification code. Although in this paper, he worked on a slightly different setting, but if you use his technique, you can get the strong converse for the overall input case, not hard, not a very complicated arguments. So I'm going to talk about achievability and also the strong converse which lead to the quantum Shannon theorem. So for the achievability, the idea is that in information theory, if you don't know how to do coding, then you do random coding. So here the random coding, just choose a random code book, and each code word is IID identically picked from this target distribution, target input distribution P. And in expectation, it just gives the target output, channel output we want. And then it's basically a law of large number. You know, if you increase the number of M, you average in these random outputs, then you are going to approximating the WP we want. Then instead of consider the worst case error, that's the minimal error, we consider the expected error. In this expected error, by the idea of random coding, if there is a random if the expected error is small, that means there exists some code book which achieve the small error. And that means our resolvability error, which is the minimal possible error, is also small. So it was earlier joint work with Hao Zhong that we estimate this expected error by using random code word. And this can given by the exponential with some sandwich range mutual information minus log of the cardinality. And then if you plug in this one shot estimate into the n shot case, then it's clear that if you have R, the rates, which is basically the log of mn in the n short setting divided by n, if we have this greater than R, or have the, say, have this one equals to R. If R is greater than mutual information, then we immediately see exponential decay from this estimate. This is for the fixed input. And for the vortex inputs, of course, we take the n-short case and optimize over all input of our one-shot estimates. And the key things here is that we take the largest possible error, then we can put this supreme into the mutual information, and that's just the range whole level quantity for the classical quantum channel. And thanks for the work by Andreas and Mark Wilde and Dong Yang, and we know this quantity is additive. They prove it for entanglement breaking, but the same arguments also for classical quantum. So since it's additive, then we just have this simplified, and you can easily see the exponential decay for the vortex input setting also. So let me emphasize that if you just naively use the achievability of a fixed input setting, it does not automatically imply the vortex input, because you can even compare if you just take a supreme of the rate in the fixed input setting, it's not always equal to the channel capacity. So that means that asymptotically, the optimal, the vortex case may not appear in the IID inputs. But in our case, what we use is some one-shot estimate plus additivity, which gives the achievability. Okay, so this is about achievability, and the converse for the vortex input setting, since it's essentially from Luber's paper, I will skip that. I will then go to the second part, which is a new version of a quantum Shannon theory, which this idea of quantum Shannon theory has already appeared in the morning's talk, which is great. But let me try to formulate this in the Shannon's original format of his theorem. So Shannon's theorem is about empirical distribution. So if you have n string of from some alphabet, you just count how many positions a letter appear and dividing by the number of the total letters. So this gives you the empirical distribution. The Shannon theorem says that if you're given a probability distribution Q and some, say, convex set in the distribution, in the state space, if you count the probability of the string that's its empirical distribution belongs to some subset S, and you count this set's probability according to IID of another of some distribution Q. Asymptotically, this probability is exponential decay, and the decay rate is given by this infimum of relative entropy. So here's a typo. This should be a P, and P come from S. So this is the the classical Shannon theory is a large deviation theorem about the empirical distribution. In particular, if this one also works in the continuous variable setting, and in that setting, it actually implies the famous Klammer theorem, which is a large deviation for the empirical mean. When you have an empirical distribution, you just take the integral, you get the empirical mean. So it's stronger than that. But this theorem also says something very interesting related to information theory, is that what are the sets what's an imaginable set about the empirical distribution? That's exactly typical set, right? The typical set is you define it through empirical distribution. So actually, in the proof, this can be reformulated by just the probability on a union of a typical sets is exponentially decayed. And if one just choose this is a typical set with some error tolerance to one particular probability distribution, this gives the Stan's lemma for two states. And then there already existing quantum extension of Shannon's theorem, which follows more the hypothesis testing approach. This has been explained in Ludovico's talk. Here I just briefly recapture it, is that we just take the now we take the first hypothesis is the fixed state sigma tensor n. The null hypothesis is rho tensor n, but rho choosing from a family, choosing from some subset of the states. And then you can consider this type 2 error. And the Bilakovich in 2000, Bilakovich and Corso in 2004, they proved this quantum Shannon theorem, which is basically say this type 2 error decay exponentially with the rates given by this minimum of relative entropy. As explained in Ludovico's talk, the proof of this one is basically trying to reduce to the classical case. You're trying to find the good measurements or good basis that you can reduce the problem to. So this is more from the hypothesis testing aspect of Shannon's theorem. And also later in Wednesday, that's I think Kun, he will also talk about some analog of this in a different aspect. But you can see that what is missing in this picture is what are the empirical distribution. So there's no empirical distribution formulation in this format of quantum Shannon theorem. But it's actually already a question as what are the quantum empirical distribution. So this is what Masahiro Hayashi tried to come up with. So the naive thing is that if you want to talk about the distribution, of course, you will need to have certain basis. You need to have a classical system. So you fix a basis. Then you can talk about all this concept of empirical distribution as just with respect to this classical system. But that's not enough because in quantum, in a quantum system, you know, not all states belong to a fixed basis. So what he adds as additional data is from this Schur-Weyl duality. So this Schur-Weyl duality says that you have n copy of a Hilbert space, then you can decompose it according to the irreducible representation of the special unitary group together with the permutation group. And then this direct sum, this decomposition is indexed by this Young index. Then what Masahito trying to do is that you first just take the standard typical subspace for this fixed space is B. But besides that, you add also the projection subspace for this coming from this Schur-Weyl duality. And remember that since your states, since this typical subspace, the empirical distribution from empirical distribution is automatic symmetric. So these two projections are commuting. So basically, you are using two compatible measurements in this projection, and then he use this lambda dividing by n become a classical distribution, together with the rho, which is the state from the B basis, together as data for quantum empirical distribution. That's his idea. Then he be able to show that if you use these ones, use this like modify the typical subspace with Schur-Weyl data and the typical the type, then you can show that if you try to measure another states with this typical space, the probability or the trace decay exponentially with some with some divergence. And this divergence is defined using some limits with renormalization to the sandwich-Ranye divergence, sandwich-Ranye relative entropy. And it's actually a new quantity. That this quantity reduced to the KL divergence in the classical case, and in general, it lives in between the standard relative divergence and the D mean. But it's a strange quantity. It does not satisfy data processing. So, but in terms of exponents, it's at least positive if you choose data difference. So it gives the exponential decay behavior. So that's what this new version of quantum Shannon theorem says. How much time I still have? Okay, thanks. Good. Okay, then finally I back to the missing piece in the channel resolvability. So this is a strong converse for the fixed input setting. That's basically we show if you're trying to do the resolution with the rate below the minimal mutual information we need, then the error will goes to 1. This is strong converse. The idea is to using this typical, modify the typical projection together with such subset which describe rho and rho prime are close, but it describe this closeness first with the quantity use relative entropy, and also use the quantity with the entropy difference. But this is just an entropy way to describe rho and rho prime should be close. And then we want to estimating a lower bound of trace distance. The way you want to do is you come up a good projection and evaluate the trace. So the test projection we use is defined by this one. This is inspired from the 2014 paper by Masahito and Shun, Professor Watanabe. But the key difference is that in the classical case, firstly, you don't need this pinching, but this is not even the most challenging part. In the classical case, you just need to use some very standard typical subspace. But in the quantum case, you have to use this very complicated one. But I will show you how this works in the next slides. So this is a little bit technical, but I will just make it brief. So basically, you just want to plug in the trace measurement duality into this trace distance. So we are using this projection. And together with the 1 minus, you can simplify this by these two traces. And these two traces each decompose into 2 terms. Then we end up with the first term. We further decompose it into 2 pieces. So this is the most most important parts. The first part comes from what we call a bad code word. This is a sanity check. Like if you want your output code word, if you want this code word is very close to the WP tensor M, then it's empirical that its average should close to a single copy, right? If it's a good code word, if these two are very close, and this distance should be small. So if even the average is not close, then it's definitely something not good approximation. So then we call this set of code word bad code word. And for this bad code word, that's exactly the place we use the Shannon theorem. You can see that's by some symmetrization trick that you can replace this by some ID copy of states. And then with that, you can using this Hayashi's new quantum Shannon theorem to get some exponential decay factor. And then the size of this summation, cardinative summation is only polynomial. Then you get exponential decay. This is where we use the Shannon theorem. And for the other side, for the good code word is exactly, we have, in a good code word, basically you have the empirical output is very close. By using this empirical output close, you can, by some standard pinching arguments, you get the rates simplified to some exponential factor of these two. And this should be very close to our rate when by continuity. So then when this is, we can choose this delta small enough to make sure this one is positive. So then you have also this one is exponential decay. Okay, to summarize that we proved we solved this channel resolvability question for classical quantum channel, and there's a new technical tool. This is quantum Shannon theory by using the typical subspace that's input that together with the typical space and the shear wire duality data. And there's a question is that since we find out the rates of this task is also mutual information, actually Haozhong wondering that's whether there's some operational meaning between the channel resolvability and the channel simulation, which is, or the channel coding, because they have the same rates. We wonder whether there's some operational connection. And for that, I would like to thank you.
I guess we have time for a quick question or so.
Right, yeah, thanks for the talk. So I have a difficulty understanding intuitively Hayashi's Sanov theorem because, like, for example, for hypothesis testing, we didn't need that to get the optimal exponents in the quantum case. We just use kind of pinching and then you do classical kind of typicality, essentially. Yeah. So first of all, like, why do you need it here? That's my first question. And second one is like, why is this optimal? Because it's, if you apply this new Hayashi-Sanov theorem kind of naively, you don't even get the optimal exponents for hypothesis,
right.
for example.
It's a different quantity.
Yeah, why do you need it, and why is it optimal for you in this resolvability case? That's my question.
Okay, so the reason we need it is that if we don't use this typical projection, we will get rates is smaller than what we need. We basically get the mutual information, but with the B part with the pinching. If you follow the pinching arguments, we are not getting the correct rates. So basically here you add a little bit more data so that you can get the desired rates. And the second question is that whether it's enough. My understanding is not the full picture you can get for what is mean for quantum empirical distribution, but it add a little bit more data, which help in this case. Maybe there's other ways you can add even more information. You can have you see that this is only the idea of this typical projection is just one basis together with shear wire duality. But still, you cannot just rely on these two information to recover all the thing or all possible states. You see, I feel that maybe there's more you can try to go with the typical subspace set. Yeah.
And shout. So, what's the example for violation of data processing for this new Hayashi divergence?
I remember there's some. I cannot remember the concrete example, but I think it's pointed out by the reviewer. It says this does not satisfy, and
It's
actually
not apparent that it satisfies, and probably it doesn't. But
I think the example I just cannot recall it now, but by some pure state, one of it is that's a pure state, then it's not satisfying. Yeah, but it's clearly there's a very visible example. Yeah.
Sorry, so you mentioned a new divergence where S goes to 0, that in the classical case coincide with the KL divergence?
Yeah, in the classical case, you can write down, yeah.
Do you get a closed form for that? Because it seems to me that it's equals to the reverse sandwich relative entropy for alpha going to 1, and that has a closed form.
In the quantum case, we don't have a...
Yeah, I think it has a closed form. If you check alpha Z Renner relative entropies paper.
So you think in the quantum case there's a closed form?
Yeah, with the principal minors of your state.
So what is called reversed?
So it's the limit of the reverse sandwich relative entropy for alpha going to 1.
Okay, cool. Thank you. Yeah.
we're a bit over time, so let's thank the speaker again.
Thank you.